Hello and welcome back again. Now I want to discuss how we can measure the properties of long-lived particles in our detectors and how this determines the typical layout of a particle physics experiment. I will stick to general concepts here without going into details of detection technologies that we employ. These will be discussed in the following lectures by my colleagues and myself. Now we have just seen how, in order to reconstruct these short-lived particles that are interesting for our physics analysis, we have to detect and measure their long-lived decay products. And we have seen that we want to measure the direction and the magnitude of the momentum of these particles, that we want to measure their energy, and that we want to determine what type of particle they are. Now, there is no single detector technology available that could do all these things, so we have to use a combination of different types of detectors in our experiments. We can use tracking detectors in order to measure the direction of flight of charged particles. And if we put these tracking detectors into a magnetic field, we can also measure the magnitude of the momentum of these particles. We can use calorimeters in order to measure the energy of both charged and neutral particles. And we will see how we can use the combination of information from different detectors in order to distinguish between different particle types. And remember here that there is only a small number of types of particles that live long enough to actually leave a trace in our detector. And these are electrons, muons, pions, kaons, and protons and antiprotons. We can use tracking detectors in order to measure the direction of flight of charged particles. And this is because charged particles interact with atoms in the detector material, which can lead to the creation of free charge carriers. For example, through the ionization of atoms in a gas, or through the creation of electron-hole pairs in a thin layer of silicon, as shown in this sketch here on the right. If we apply an electric field across the detector volume, we can collect these charge carriers and we can measure the signal that these charge carriers induce on segmented electrodes. If we know which electrode has seen a signal, we know where the particle has gone through the detector. And if we now put several detection layers one after the other, we can combine the information from these different detection layers in order to follow the trajectory of the particle. One thing that is important here is that we put as little material as possible in the way of the particle that we want to measure, because any energy loss and any multiple scattering that this particle suffers along its way will deteriorate the precision with which we can measure its properties. We can measure the magnitude of the momentum of charged particles if we measure the bending of its trajectory in a magnetic field. The bending of its trajectory is of course caused by the Lorentz force, which acts on any moving charge in the magnetic field. And this simple equation here, calculation, shows that the bending radius of the trajectory is actually simply proportional to the momentum of the particle. So if we can measure the bending radius and we know the magnetic field, we can determine simply the momentum of the particle. Now, one thing that you will notice if we look at this event displayed at the right is that there are particles that are bent clockwise and there are particles that are bent anti-clockwise. And this is of course due to the fact that the Lorentz force acts in opposite directions on positive and negative charges. So by looking at the direction of the curvature, we can determine the charge of the particle. So we can, for example, distinguish between positive and negative muons. In calorimeters, we want to measure the energy of particles. We use dense, high Z material as an absorber so that the incoming particle interacts heavily with the material, creating a shower of secondary particles. And the higher the energy of the incoming particle is, the more particles are created in these showers, the larger the signal that is created in the detector, and from the measured amplitude of the signal, we can then reconstruct the energy of the incoming particles. Electrons, positrons, and gammas create showers by electromagnetic interaction. so electrons and positrons through Bremsstrahlung and gammas through pair production. And these showers are best measured in so-called electromagnetic calorimeters. Hadrons do not create Bremsstrahlung, but they create showers via hadronic interactions. And these showers look very different, and there's a different type of calorimeter, hadron calorimeters, which are optimized to measure the shower of hadrons. Now, how these different detectors are arranged with respect to each other depends on what type of experiment we are looking at. In a colliding beam experiment, where we collide two beams head-on with each other, the collision happens at rest in the laboratory system, particles are produced in all directions, and the detector needs to cover the full solid angle, it's also called often a 4 pi detector, if we want to detect all the produced particles. This is usually implemented in the form of a barrel detector, as depicted here in the sketch on the right, which is then complemented by end caps before and after the barrel. But the barrel is certainly the most important part of the detector, and this consists of concentric layers of cylindrical detectors. The innermost detector is always the tracking detector, then you have the electromagnetic calorimeter, then you have the hadron calorimeter, then you have the yoke of the magnet that is used to create the magnetic field inside the tracking detector that allows you to measure the momenta of charged particles. And then on the outside of the magnet yoke you have muon chambers, which you can use to identify muons. In a fixed target experiment, we shoot a beam of particles into rest at a target at rest. There is a Lorentz boost of the collision in the laboratory system, which means that all the particles are produced in the forward direction. So we need to equip only the forward direction if we want to detect all particles. And that leads typically to a layout as the one that is shown here, where we have planar detection layers orthogonal to the beam axis. But the order of the detectors is very similar. So we first have a tracking detectors here, we have a magnet in which we bend the trajectories of charged particles in order to measure their momentum. Then we have an electromagnetic calorimeter, we have a hadronic calorimeter, and finally we have a muon system in order to identify muons. Now we want to look at how different particles interact in these detectors at the example of the CMS detector at the LHC. You see here a photograph of a cross section of one of the slices of the experiment, and this is a simple sketch of this, and now we are cutting out one slice of the cake here, which has all the different detector elements of the CMS detector, and we will see some sketches on how different particles behave in these detectors. So this is this cutout here. You have here on the left, you would have the beam axis here where the collision takes place. This is surrounded by a tracking detector to measure the trajectories of charged particles, followed by an electromagnetic calorimeter, followed by a hadronic calorimeter, followed by a solenoid, the coils of a solenoid magnet, which creates the magnetic field to measure the momentum of charged particles here. And outside the solenoid magnet, you again have these muon chambers. So how do different particles now look in these different detector elements? Looking first at an electron is a charged particle, so it will leave a trajectory in the tracking detector. The trajectory will be bent, the bending radius will depend on the momentum of the particle. Then it will create an electromagnetic shower in the electromagnetic calorimeter, and from that we can measure the energy of the electron. If we have a charged hadron will also leave a trajectory in the tracking detectors. It will again be bent because it's a charged particle. It will not deposit too much energy in the electromagnetic calorimeter, but it will shower up in the hadron calorimeter. If we have a muons do not deposit much energy in the electromagnetic calorimeter because they are much heavier than electrons, so they do much less Bremsstrahlung. They will also not create showers in the hadronic calorimeter because they are not hadrons, so they do not do hadronic interactions. So they essentially pass the whole detector, and they are the only types of detectors that will leave hits in these muon chambers outside of the yoke of the magnet. And that is why these detectors are there, because they help really to identify muons. Muons are very easy to identify, and for that reason we love them in particle physics experiments. You will notice that the trajectory of this muon is curved in one direction in the inner part of the inside of the magnet yoke, and then opposite outside of the magnet yoke. And that is because the direction of the magnetic field goes in opposite directions inside and outside of the yoke. Now we look at another experiment at the LHC, the LHCb detector. And this LHCb detector has essentially similar detector elements. It also has tracking detectors. It also has a magnet to measure momenta. It has electromagnetic and hadronic calorimeter. It has muon detectors. But there are important differences. One is that we have, in addition to these detectors, we also have Cherenkov detectors, one here in front of the magnet and one here behind the magnet. And the second big difference is the geometry of the detector. In this case here, we do not see a slice of the detector. This is the full experiment, and it looks actually like a fixed target experiment. Although LHCb is a colliding beam experiment at the LHC, it has the geometry of a fixed target experiment. And I will explain in a minute why that is so. So, why do we have Cherenkov detectors? This is to essentially help with identification of particles. So to distinguish between the different types of particles, we exploit the different interactions of the detector materials. We have seen that electrons and positrons shower by electromagnetic interaction and create a shower in the eCal, whereas pions, kaons, protons and antiprotons shower by hadronic interaction and create a shower in the HCal, whereas muons do not create showers at all and are seen in muon detectors. So by looking at these different signatures, it's relatively simple to distinguish between electrons and muons and hadrons. But it's not at all trivial to distinguish between the different types of hadrons here. And this is not very important for many of the physics measurements that are done in the CMS experiment, but this is extremely important for LHCb. And that is why in LHCb we have these additional rich detectors in order to be able to distinguish between protons, antiprotons, between pions and kaons. In order to distinguish between these particles, we have to measure essentially their speed, because if we measure their momentum through the bending of the trajectory in the magnetic field, and we measure their speed, we can calculate their mass, and when we know their mass, we know their particle type. There are different ways to measure the speed of a particle. The simplest one is time of flight, so you measure just how much time does it take the particle to go from one position to another position. This works well at low speed, but as soon as you go to very high speed, the differences become just too small and you cannot measure that anymore. The second possibility is to look at DEDX. The Bethe-Bloch equation that you have studied tells you that the energy that the particle loses in a detector depends on its beta, but this also works mainly at very low values of beta, where the DEDX really depends strongly on beta. If you go to very high beta, the dependence is not very large. So the best way to actually distinguish between different types of hadrons at high beta is Cherenkov detectors. And you see an example here on the right from LHCb, where we have plotted on the horizontal axis here the momentum of a particle that has been measured in the tracking system by the bending of the trajectory in the magnetic field, and on the vertical axis is plotted the Cherenkov angle, the angle under which Cherenkov light has been measured. And you see these clearly four distributions here, one here for protons, one for kaons, one for pions, and here one for muons. So by combining the information from the momentum and the Cherenkov angle, we can clearly distinguish between these different types of hadrons. Now, in case you are not familiar with the concept of the ring image Cherenkov detector, a Cherenkov light is always created when a charged particle traverses a medium at a speed that is larger than the speed of light in that medium. In this case, the dipole oscillations that are excited by the charged particles lead under a certain angle to a positive interference, and you get a shock front, a light front under this angle. This is a little bit similar to the shock front that a fighter plane creates when it moves at a speed that is larger than the speed of sound in air. The angle under which this shock front is produced depends on the speed of the particle. So if we measure this angle, we can calculate the speed of the particle. And that is exactly what we do in a ridge detector. And Andrei Goludvin will discuss this with you next week. So the second thing that was special about the LHCb experiment was the detector geometry. So why does LHCb look like a fixed target experiment when in fact it is a colliding beam experiment? The reason for this is that the main goal of LHCb is to study decays of particles that contain a B or anti-B quark. And these particles are produced mostly under small angles with respect to the proton beam axis at the LHC. And you see the distribution here plotted on the right. So you see here the polar angle of one of the B quarks versus the polar angle of the second of the B quarks here. So this is the angle with respect to the beam axis. And you see that most of the particles here are produced at very small angles. In the one direction, the whole thing is symmetric, so you would have the same also in the other direction. So for LHCb, it's much more efficient to just cover this forward range angles where the particles that we are interested in are produced. So this is an important message, that experiments are always optimized for the physics processes they are meant to study. And that is why you will never find two particle physics experiments that look exactly the same, because each experiment has its specific goals and it will have been optimized to meet these goals. So why are these B and anti-B quarks produced under small angles with respect to the beam axis? Here we come back to something that we discussed already in the context of production of Higgs bosons. The B and anti-B quarks pairs are produced not in the interaction of two protons, but they are produced by the interaction of two of the gluons inside the proton. And you may remember that these gluons inside the proton carry only a small fraction of the momentum of the proton. Now it is very likely that one of the two gluons that collide with each other carries a larger fraction of the momentum of its proton than the other. So this leads to an asymmetric collision. Although the collision energies of the two protons are the same, the collision energies of the two gluons are different, and therefore you get a Lorentz boost, either in the one direction or in the other direction. So this brings me to the end of this part of the lecture, and I have again my quiz for you here. I think the first two questions should be trivial to answer looking at the slides. The third question requires a little bit of thinking, and we will discuss this certainly when we meet next week. Thank you very much.